Hey everyone, today we are going to finally solve an environment using policy iteration. So you should now be comfortable with the Bellman equation. We've briefly taken a look at the Bellman optimality equations. If you're confused about any of this stuff, go ahead and take a look at the previous videos because I'm just going to assume all of that is known knowledge. But we've looked at two variants of the Bellman equation. There's the Bellman expectation equation, where we're essentially to compute the values of a state, or the value function for all the different states, we need to take an average over the policy. So this is an expectation because we're doing a weighted sum of our, if you again remember, all of this stuff here is basically our Q values for some given state action pair. Again, if you're confused about any of this, just please go ahead and take a look at those earlier videos. I don't want to repeat the same thing too many times, but we have essentially a weighted average here, right? A weighted sum over this policy. But we saw that there's a limitation here. To solve this equation, it requires that we actually have a policy. But the policy is what we're solving for. In an environment, what we want is to answer the question, what action should I take given the state that I'm in? And so the thing we want is in the equation that we need. So we can't just directly use this. We're going to have to use a trick, and we're going to take a look at that in a bit. The Bellman optimality equation allows us to get the same optimal value function without the policy. Notice there's no policy pi in here. It's just a max over a. And in the previous video, when we looked at the Bellman optimality equations, we saw that you can indeed, though we didn't go into the specifics, you can indeed derive that this can get to your optimal value function essentially using the fixed point theorem. But I don't want to get into too many details there. But we have these two variants, and these two variants allow us to solve our environment in two different ways. The first way is policy iteration. So if we're doing the expectation equation, right, when we actually need our policy, then we have to use a method called policy iteration. And it's pretty straightforward. Let's go ahead and just, if we don't know what the policy should be, why not just start with a random policy? And then we can also go ahead and initialize the values as 0. And so there's two steps. Step 1 is the policy evaluation method. And what this is going to be is for this random policy that we just went ahead and just created because we don't know any better yet, go ahead and compute the values of the policy. So that's this, right? This equation allows us to compute the values of our game given this policy. And so we can go ahead and compute the values given that policy. Once we've computed those values, we can use those values to improve our policy. So this will allow us to update our policy. And then we're going to take this improved policy and evaluate it again. Using the evaluation, we'll compute our values, and with our new values on the new policy, we're going to improve it again. And we're going to repeat this over and over again until we converge. So that's policy iteration. And that's what we're going to be focusing on today. Next time, we'll be looking at the value iteration. Value iteration is a slightly different way, and it uses the optimality equation, where let's just go ahead and notice there's no policy here, so all we have is values. Let's go ahead and initialize the values as 0. We can then compute the optimal values for our game directly, and then once we have the optimal values, just go ahead and derive the policy from those values. And so this method we'll look at next time. It's actually a little bit simpler. We're going to look at policy iteration today. And so in policy iteration, there's two steps. Step 1 is policy evaluation. And all I've done here is convert my problem to an iterative one. So k and k plus 1 here is the iteration index. So this is, it'll be more clear when you look at it like this. When we look at our values, we're going to initialize it. This is just going to be initialized as 0s. We're just initialize our values as 0s. We're going to solve some stuff. You'll see kind of how this is implemented. And we'll get our value at the first iteration, and then we'll plug that in, repeat again, get the second iteration, plug that in, repeat, get the third iteration, ... And then once the values at some k plus 1 iteration minus the kth iteration, so 2 preceding ones, is less than some tolerance, then we'll say that our values have converged. It has converged for this specific policy. Once we have our values, remember our policy, our goal is to select the action that maximizes our future rewards or maximizes our values. So do exactly that. To derive my updated policy, just select the action that maximizes my future rewards for that state action pair. So again, this is basically just the Q values, right? The Q values. It's this expression right here. Again, just take a look at the previous videos if you don't remember why. But what we're trying to do is just select the action that maximizes my future expected rewards. And that will give me my new policy. Once I have my new policy, go back, plug it in here, use the new policy and recompute the values. Once you get your updated values again for the new policy, go back. Let's improve it again. And we just go back and forth until our policies have converged. And again, remember, this is still a model-based method. This right here is our transition probability. What's the probability of getting to some state given that we took an action at our starting state, right? And of course, the reward. So this is a model-based method because we need these transition probabilities. And so that's a key idea. We're going to be looking at model-free methods like T-learning, SARSA, Q-learning, and all that stuff in the future. But for now, we're going to be looking at policy iteration today and value iteration next time. So let's go ahead and just implement it. So implementation is pretty straightforward. I do want to do a quick recap, or if you've never seen it before, how do you use the OpenAI, or I guess I don't think OpenAI actually runs Gymnasium anymore, but it used to. But how do we use Gymnasium, which is the package we're going to use for our environment. So Gymnasium, if you don't have it, you're going to have to install it, but it's pretty easy. They have instructions online. This should be a simple pip install, but import Gymnasium as gym. We're going to need to be able to plot stuff. Import matplotlib.pyplot as plt. And we need from ipython.display, import display, and clear. I guess we don't really need clear output. We're just going to keep it simple. So we just need to be able to visualize the game. And so how do we use this environment? It's pretty straightforward. I'm going to go ahead and create an environment. And we're going to do gym.make. And basically all the environments in the Gymnasium package all work functionally the same way, right? So we're going to do frozen, lake, v1, and we're going to select the map name is going to be the 4x4 map. So we're going to be using the 4x4 map where there's 16 possible states that you can be in. So there we go. And we're going to say the render mode is going to be RGB array. This will allow us to actually visualize what's going on. And then is slippery equals false. So this won't be a slippery environment. We'll get back to that later. But a slippery environment means that if you take a step, right, let's say I want to go down. That's the action I selected. There's 4 actions available to me. I can go up, down, left, right. So let's say I select to go down. In a deterministic environment, if I want to go down, I will go down. With 100% probability, I will go down. In a stochastic environment, if I say I want to go down, I could slip and go in a different direction, right? Because there's some randomness there. But for now, we'll be dealing with a deterministic one, and we'll get to the stochastic one a little bit later. So there we go. That's our environment. And we can check a little bit about this environment. You can do env.observation space. And this is going to be 16, right? There's 16 possible, because it's a 4x4 grid, so there's 16 possible locations I could be in. And then there's env.action space. There are 4 possible actions that I can take at every single state. And so there we go. So I've gone ahead and just created a quick dictionary here of the index. So there's action 0, action 1, action 2, action 3. Those are my 4 actions, and they're left, down, right, up. Those are my actions. And so how do we use the environment? Let's kind of do a quick example here. So we can do observation. And it also returns some additional information that we don't typically care about. And then we do env.reset. So what this is it's going to go ahead and start a new game. env.reset will start a new game. And we can take a look at our observation, and it will be 0. Because at the beginning of the game, we are at location 0. Because the game goes location 0, 1, 2, 3, 4, 5, 6, 7, ... right? Just like this. I guess the index here I started at 1, but in the game, they start at 0. 0, 1, 2, 3. So we're starting at 0. Now that we have our observation, it'd be good to be able to just visualize the board a little bit. So I just have this quick helper function here. I'll just copy it in, nothing crazy. And it's just to render the board. It will do env.render. It'll create basically a NumPy array of the game. And then we can use matplotlib to actually plot it. And so you do render board. And there we go, right? That's what our game looks like. And we're starting at index, or basically state, 0. Now that we have that, let's just play a game. We can do for blank in, or we don't actually need to do any of that. Let's just keep it simple. Let's pick an action. Let's say action is equal to env.action space dot sample. So what we're going to do is randomly, because obviously we don't have a policy yet, later we will, but right now we don't have a policy, so let's just go ahead and randomly sample an action, up, down, left, right, from the 4 actions available to us. And so in this case, we selected action 2 as the thing we randomly sampled, and action 2 is move to the right. Okay, so let's go ahead and do that. So we're going to do that. We're going to actually use this action, and so we can do env.step action. And what this is in this environment, I want to perform this specific action. And when we do this, it's going to return some information to us. It'll return the observation, right? So what is the new state that we're at? So we started at state 0, we moved to the right, we should end up at state 1 now, right? But we'll see that in a bit. So what's the new state that I'm at? What reward did I get? Is the game over? And then truncated, which we don't really care about right now, but the idea is that the game is over. So these both are Booleans. The game is over if I either fall into one of the frozen lakes or I make it to my present, right? So if I do either one of those things, then the game is over. And truncated, just make sure that the game doesn't go on for too long. So you can imagine that if my MDP decides to just keep going in circles over and over and over again, or not my MDP, but my agent decides to go in circles over and over again, then at some point I might go for like 1,000 steps or 10,000 steps or whatever. We want to avoid that. So the game is over if you just go in circles and like just move around and never make it to the goal state or into any of the frozen lakes. So that's just a truncated flag. And there's a default truncation already set. So we can go ahead and take that step, right? So this is me taking a step, and this will print out observation. So as expected, we should end up in 1. Because we started in 0, we moved to the right, so now we're in state 1. We should have gotten a reward. In this case, the reward's just 0. We only get a reward at the end of the game, so I don't have it here, but the reward function for this game is basically it's 0 reward everywhere and 1 reward for getting to the present, right? So that's our rewards. So in this case, it's 0. And then done and truncate is fine. We haven't fallen into anything, so we're good. We can again do render board, and we'll see that we have moved to the right. And so that's the game. And so as you play the game, our goal is to be able to get to the end, And so let's go ahead and look at what our MDP looks like, because this is a model-based learning method, right? We're going to be using policy iteration and value iteration in the future, are both model-based methods. So we need the Markov decision process for this environment. And to get that, we can do MDP is equal to env.unwrapped.p. And it looks like this. Basically, you have for every state, so state 0, state 1, state 2, state 3, all the way up to state 15, you have a dictionary. So it's a dictionary of dictionaries. At state 0, if I take action 0, I will with 100% probability end up at state 0. I'll get a reward of 0, and the game is not over. Or at state 0, if I took action 1, I will with 100% probability end up at state 4. So taking action 1 is going down, right? So we'll end up at state 4 because it will be, if we're here and we go down to this state, that's 0, 1, 2, 3, 4, right? So going down to 4. And again, we'll get 0 reward and the game is not over. What about a game ending state? Let's take a look at this one. So this would be state 14. And if I'm in state 14 and I go to the right, then I will get a +1 reward. Is that true? Let's check. So at state 14, if I go to the right, which is action 2, then with 100% probability, I'll end up in state 15, which is basically the state with the present in it. And I'll get a 1 reward. And the game is over, as you can see. Similarly, if I'm in state 4 and I go to the right, I'll fall into a lake. So let's just check that. So if we're at state 4 right here, and if I go to the right, take action 2, I will, with 100% probability, end up in state 5. And state 5 is an ice lake, and so, or the frozen lake. And if I fall in there, then I get 0 reward and the game is over. And so that's my MDP for a deterministic environment. Now we can also have a stochastic one. A stochastic environment is me saying, hey, I want to move down. But the way that they built the stochasticity into this environment is if you want to move down, 1/3 of the time you will actually move down. But 1/3 of the time you'll move in 2 of the perpendicular directions. So if you want to move down, then one third of the time will move down, but then one third of the time will go either left or one third will go right. And so which direction you go is kind of unknown, right? So there's some randomness in the environment. And we'll be dealing with that a little bit later. But let's go ahead and just take a quick look. Yeah, we'll look at that in just a second. So yeah, let's create a environment. So to create an environment with randomness, we can do env is going to be gym.make frozen. Actually, we can just copy the one from above. It's the same thing. It's going to be exactly the same thing. Right, it's going to be this. But now we're going to set slippery to true. And so now when we do env.unwrapped.p, this is going to return a slightly more complicated setup, right? This is what it looks like. And so now what this is at state 0, if I take action 0, right? So if whatever it may be, if I take action 0 with 33% chance, or basically one third of the time, I'll end up in one place and I'll get this reward. And one third of the time, I'll end up in this other place and I'll get this reward. And one third of the time, I'll end up in this other place and get this reward. ... So we can see that taking an action is no longer with 100% probability like we had here, right? With 100% probability, we end up at the next state. It no longer looks like that. It's going to be basically, it's split up. It's split the probability between all the possible places I could end up in. Because even though I say I want to go, for example, let's look at state 14 again, right? State 14. I know at state 14, if I take a right, so I want to take a right, if I actually end up taking a right and end up in state 15, then game's over. But I could also not end up taking a right. I could end up going in a different direction. I could either try to move, I might end up moving down. So if I want to move to the right, then there's two possibilities. I could either go up or I could go down. If I try to go down, then I'm still stuck at state 14. So fine, there we go. On the other hand, if I try to move, I could also move up. I could go back up. So if we look at this picture again, if I'm at state 14, with 1/3 probability, I'll actually end up at my goal state. But with 1/3 probability, I'll end up going up, or with 1/3 probability, I might end up going down. So we have some stochasticity in the environment, and it leads to a slightly more complicated looking MDP like this. And so we'll kind of see how we can work with this a little bit later. So let's go ahead now and implement policy evaluation. So policy evaluation. And this is going to take some information, right? We have our policy, right? What is the policy we want to compute the values on? We need our gamma, right? 0.99. If you remember again, in our policy evaluation, we have our gamma, our discount factor. We have the policy that we want to compute the values on. So we just need to make sure we pass all these things in. And we also want to, as we're iterating, we need to make sure we set some tolerance for epsilon, right? So when are we done? And so we're going to set all that stuff here. How many iterations? We're going to say iterations is 1,000. And we're going to say our tolerance is 1e negative 10, let's just say. So once our values stop changing by that much, that means we're done. And so like I mentioned, we first want to initialize our values as 0. So we're going to say v is equal to np.zeros, env.observation space.n. We're going to initialize it as zeros because we don't know any better just yet, right? And what we're going to do is iteratively improve our estimate for the value given this policy. Now, one thing to keep in mind is our policy is a deterministic policy. There's also stochastic policies. We're not going to be dealing with any of those right now. But a deterministic policy basically says at this state, with 100% probability, you should take this action. A stochastic policy would say, oh, at this state, you should 80% of the time take this action, but 10% of the time take this other action, yada, yada, yada. I'm not going to worry about kind of extra complications like that. We're doing a deterministic policy today, so it's going to be at this state, you will 100% of the time take this action, which actually simplifies our life a little bit because that means this policy here, which is a probability of A given S, is going to be 1 for the action we selected and 0 for all the other actions. So that means this sum here actually gets simplified quite a bit, and it basically becomes 1 times something for the action selected and 0 times something for everything else. And the action selected in our case is determined by our random policy. That's going to be, oh, take a left here, take a right there, dot, dot, dot. And so let's go ahead and do that. So we're going to first do for blank in range iterations. And this is an iterative method, right? So let's go ahead and create a copy of this v. So we're going to call it vk for now. And we're going to create a copy np.copy v. We're going to create a copy of it. And now that we have a copy of it, we want to compute the value for every single state. Remember, this value function is for every single state. So we need to loop over all the states and make sure we compute this. So we're going to do for s in range env.observation space.n, right? So this is going to loop from 0 to 15 basically for the 16 states that we have. And then what we're going to do is, what is the action selected? Our action is going to be determined by the policy, right? The policy determined our action. So let's just go ahead and grab it. Our action is going to be our policy at state s, right? So at this state, what is the action that we selected? And there we go. That's the action, or the policy selected. Now that we have that, it's time to grab the transition information, because if we look at our formula again, we still need a little bit more information. We need this probability here, right? What's the probability, the transition probability of going from s to s prime, given that you took action A? And we also need our reward, right? What is the reward for taking that action? So let's go ahead and grab it. And again, if you remember, all of this information is incorporated into our MDP. So this is again an MDP for a slippery one. Let's set this to false. So it's, there we go. So it gives us the probability, the reward, the state, the new observation, and we also get our false, right? So is the game over or not? So let's actually go ahead and run this a little bit. We can do policy evaluation, and we're going to run it on this kind of randomly generated policy that we came up with. I'm going to throw a break in here and a break in here. So print action. This policy for state 0 decided to take action 0, which is going left. So there you go, right? That's our action. And what we want is to see the MDP for this state in action. So we can do env.unwrapped.p, and we're going to index it for this state, and we're going to index it for this action. So let's go ahead and do one at a time. Let's do print. So this is the MDP, right? So at state 0, if I take action 0, this happens. If I take action 1, this happens. If I take action 2, this happens, dot, dot, dot. And we already know what action we're taking because that's set by the policy. So we can also index it for the action. And we can see that this is our setup. And so this returns our probability, our next state, where are we ending up, what's the reward we got, and is the game over. And so let's go ahead and set all of that. It's going to be our probability, our S next, our next state, our reward, and terminal is the game over. Or done. You can call it whatever you want. So we have all of that. And now what was our formula? Remember, the values is equal to, in this case, this sum becomes pretty straightforward because we're not actually accumulating anything. This is just 1 for the action we took and 0 everywhere else, so we can ignore them. And so all we need to do is the reward plus the discounted future states rewards, right? So reward plus the discounted future states times our probability. So let's go ahead and do that. That's going to be our probability. So we're going to set in our VS, we're going to update it. It's going to be equal to, so we're updating our values now using our current estimate of the values. So it's going to be probability times reward plus gamma times what our current estimate of the future rewards are. So whatever we have for S next, because again, remember, this is on S prime, right? The next state. And that's the key idea. So reward plus gamma times the values of the next state, our current estimate of the values of the next state. And so that will update our V to become, basically V is now becoming VK plus 1, right? The next iteration. So we're using VK to create VK plus 1. And then of course, again, this is going to create a new copy of V, which makes this VK plus 1. Then we're going to use VK plus 2, and it'll just repeat over and over again. And so we now are updating our values, just using the formula as we kind of explored before. Now that we have that, we can do if np dot, and this is just a check, if np dot max np.abs. And what we're checking is our tolerance here. So we're going to say if the max difference between v minus vk, right? So if the max difference between these two is less than the tolerance that we set, then we are done. We no longer have to continue iterating. We've ended. And then we can return v. Looks like I missed a parenthesis somewhere. So I'm missing that one right there. All right. And I am missing right here, policy, probability s next reward. Terminal, not enough values expected for, got 1. Let's check it. Oh, right. So it's a list, right? This thing returns a list, so we just have to index it. So there you go. There you go. All right. So we can see this is our estimate for the values, which doesn't look all that helpful because nothing obviously changed. It just returned 0. We're going to see this change when we actually write the policy improvement method. But overall, this is all that's happening. You set the values, initialize the zeros, and then iteratively just use the formula that we set up and iteratively solve for it, right? Continue updating your values until you have your, until you reach your tolerance, right? So this is just making sure that the maximum absolute error is less than our tolerance, and that's it. Neat. So that's step 1, right? This is our policy evaluation method. But this on its own is not enough. Now we need the policy improvement method. So policy improvement, if we again remember, is going to be, our new policy is going to be select the action that gives us the maximum future value, right? The maximum future value. So this should be pretty straightforward, but it'll require us to actually compute the value for the different actions. So what this is going to look like is we're going to just create a new policy, just randomly create, we're going to create a new policy, and then we're going to iteratively figure out the Q value for every single state action pair. So at this state, if I take this action, I get this value. If I take this other action, I get this value. If I take this other action, I get this value, ... Repeat that for all the different actions. And then once you get it for all the actions, select the action that gave you the maximum value. So let's go ahead and do that. So that's going to be def policy improvement. And all this needs is the values function and the gamma, of course, which will leave as 0.99. So there we go. You can play with different gamma values, right? The discount factor, I just left it at 0.99. I'm sure you could get better results if you kind of mess with it. It's a hyperparameter after all. But for now, this should be sufficient. So let's go ahead and create a placeholder to fill in our new policies. We're going to say a new policy. It's just going to be env, or it's going to be np.zeros. We're just going to initialize the zeros. env.observation space.n. So it's our new setup. And now we're going to, again, iterate through all of the states. We're going to just iterate through all of our states and then evaluate the Q value of each of those states. And so it's going to be for s in range env.observation space.n. Right? So for every single state, we're going to create a thing, an empty list called QSA. And this is going to store the Q value at this state for all the different actions I can take. And so now we can do for action in range env.actionspace.n. Let's go ahead and see the value of these different actions. So just like before, we can index into our MDP. So it's going to be probability, our what's the next state we end up in, what's the reward we get, and is the game over, is going to be env.unwrapped, right? Again, .p, that's our MDP. And we want it for this state and for this specific action. And it's a list, so we're just going to index into it so we don't get index errors. And so now what we can do is compute the Q value. And the Q value is exactly what you see. It's the reward plus our discounted future rewards times our probability, just like we had before. Nothing new has happened. So let's go ahead and do that. Our Q is going to be the probability times our reward plus gamma times the values of the next state. And notice that we're just using values directly here because we're not updating the values. We're not changing the values. We're just evaluating the Q value for the different actions given this information, right? Given this value state. So there we go. We now have everything we need. That's our Q value, and we're just going to store in our QSA.append our Q value and just store that in there. And then our best action, so let's go ahead and take a look here. Policy improvement, and we're going to pass in our right here, so I'm going to call this values right there, and we're going to pass in our values. And now that we have that, let's go ahead and print out QSA and break it right here. And so we can see right now there's nothing here. So when we do np.argmax, it'll just default to the first one, I believe. But as we iterate and continue to improve, you'll actually see these numbers updating. So for now, let's just do best action. It's going to be np.argmax. What is the index of the highest value action, QSA? And then we're going to stick into our new policy. For this specific state, it's going to be the best action. That's what we select. And we're going to return our new policy, just like that. And so we can see our policy is now, we have a 2 over here. Great. So we'll kind of see. And this is actually interesting because we know that at the last state, taking a right is the best action to take. Right? We actually get reward information. And now that some of that reward information has propagated back, slowly but surely, that reward information will propagate through the entire, through all of our states. So it takes many iterations to get this correct. Okay, good. So that's our setup. So we have implemented our policy evaluation, our policy improvement, and now it's time to toggle between the two. So the policy iteration method, so we can do policy iteration, and this is just going to take some information. What is the environment we're working with? How many iterations are there? Num iterations. Equals, let's say 1,000. We're going to do 1,000 iterations between policy evaluation and policy iteration. And let's just set the gamma equals 0.99. Right, so there we go. And so just like we did before, we need to initialize a random policy, right? Because at the beginning of policy iteration, we don't know any better. So let's just go ahead and initialize a random policy, just like that. And once we've initialized a random policy, we can do for blank in range num iterations. We can do values, right? Let's compute the value of this specific policy. That's going to be the policy evaluation, right? It's going to be policy evaluation on this policy with gamma equals gamma and iterations equals num iterations. So as you can see, we're going to do 1,000. Obviously, you can mess with it however you want, but we're going to do 1,000 iterations of switching between policy iteration and policy evaluation and policy improvement. And then inside policy evaluation, we're going to use 1,000 iterations to actually estimate our values. But of course, we're just going to end it when we break tolerance, right? So when we actually get good enough where nothing's really changing. Good, so those are our values, or our estimated values for this specific policy in this environment. Now that we have that, we can go ahead and update our policies. Or updated policy is just going to be the policy improvement function we wrote, improvement on our values. And then again, gamma equals gamma. Right, so we've computed the values and used the values to update our policy. And that's the key idea. And we're going to do if np.all, if our policy is equal to our updated policy, right? So basically, as we kind of keep going, if our policy no longer changes, that means we've converged. So then we can just go ahead and break, right? We can say it's over. Otherwise, we can say policy is equal to our updated policy. And we just keep going until we're done. We return our policy, return policy, and we are good to go. So now we can do learned policy is equal to our policy iteration, and we're going to pass in our environment, and the gamma is 0.99 is what we set here. And so then we can use the print policy function, pass in our learned policy, and let's see if it makes sense. So our learned policy says that we should move down here. Makes sense? Then it says we should move down here. That makes sense. Then it says we should move to the right, which makes sense. Then it says we should move down. Then it says we should move right. And then it says, well, it doesn't really matter what we do here because that's game over. So this seems like a great policy for our model. So let's go ahead and play the game. I'm just going to go ahead and copy this in. Right? This is just going to, this code we wrote already. We're going to start a game. And instead of before, we kind of randomly selected an action from our possible actions, we're going to select our action from our learned policy. Right? So let's go ahead and play it. So here we go. We start here. We then move down. We then move down again. Okay. And then we move to the right. We then move down again. we move to the right, and our game is over, right? We made it to the end. Game over, reward 1. So this is looking promising, right? This is exactly our policy iteration method. Now, the thing is that in this policy iteration method, we did it with a deterministic environment. But now it's time to move over to a probabilistic environment. And nothing will really change in our code. It's just that we now need to sum over, so notice here, before, this probability that we multiplied by was just 1, right? With 100% probability, we would end up at that state, and that was it. And so there's really there was none of this like summing over what are the future states I could end up in, and what are the rewards I could have. That didn't really occur because, well, there's only one place you could go. But now, if we're doing a probabilistic environment or a stochastic environment, instead of just doing the sum directly, we're going to have to accumulate up this equation, basically the Q values essentially, for all the states and all the rewards I could possibly get. So nothing changes too terribly, just a couple of extra lines. So first of all, let's go ahead and do it. So we're going to do def policy, and let's go ahead and actually define a new environment here that has our slippery is true, just so we can see it. Yeah, okay, let's do it right here. So that's our new environment. And these are the things that we use to actually compute our values and the Q values in our evaluation improvement. These are the things we want to update. So let's go ahead and do that. We're going to do def policy evaluation policy gamma equals 0.99, whatever. Iterations is 1000 and tolerance is 1e negative 10. So same as always. And what we're going to do is set our values to np.zeros. And it's going to be env.observation space.n, right? So we're going to, again, same as before. When we're evaluating this policy, go ahead and initialize the values as 0. And we're going to do for blank in range iterations, right? For every single iteration, we're going to, again, create a copy. vk is np.copy of our current estimated values, which is just 0 right now. And here's the key idea. So first of all, we need to loop through all of the states for s in range env.observation space.n, right? For every single state, we have to repeat this. And here's the key idea. What is the action I want to take? Let's call this the wanted action. This is going to be whatever the policy says I should take. So the policy says at this state, I should take this action. Now we know that we may not necessarily actually end up taking that action because of the probabilistic nature of the environment. We might want to go down, we might end up going right or something. So we can look at the possible actions taken, or possible, let's keep it the same, taken actions. And this could be env.unwrapped.p. Let's look at that state, and for this wanted action. So let's just take a quick look at what this looks like again. This is going to be our policy evaluation on our current policy, which we don't actually, well, just it's fine. Shouldn't be a big deal because we had the one from earlier, but it's no big deal. It's just a randomly initialized policy. Okay, so let's look at our possible taken actions. So we can see here that it looks like there is a slight bug. So we're taking for this wanted action for this env. Oh, let's set slippery to true. There we go. So now we're saying that at the first state, with 33% probability, I'll end up at this state. With 33% probability, I'll end up at this state. And 33% probability, I'll end up at this state. Those are my options. And so what we need to do is sum up all of the possibilities over the states and, of course, the rewards, right? So we need to actually use these sums here that we didn't have before, or accumulate them in. So let's go ahead and try that. So to do that, we can do our v s, let's just set it to 0 for now, and we're going to accumulate it in. We're going to do for prob s next reward terminal in our possible action or possible taken actions, right? So we're going to loop through. So the first set of my prob s next reward terminal, the next set of the prob s next reward terminal, the next set of the, right? So we're going to loop through each one of these one at a time. And we're just going to accumulate it in. We're going to v s plus equals and the formula didn't change. It's still going to be the probability times our reward plus gamma times our current estimate of the future reward, VKS next. And this shouldn't be probability, this should just be prob, as I called it. So this is just going to go ahead and accumulate up, or just sum up, all of the possible future states I could go in, which is closer to this formula, right? That's exactly what we're doing here. Or if we look at this one, that's exactly what we're doing here. Neat. So that's our setup. That's our value. That's our estimated value for this state. And then we can go ahead and set VS to VS. So if we go ahead and take a look earlier, what we had done in our policy evaluation, all we did is compute directly. This is my estimate for the value. And it was as simple as that. But now our estimate for the value isn't just for a state, but we need to accumulate over all the possible states I could end up in, right? Because this is a stochastic environment. Before, again, these probabilities were just one. And so there were no other states I could end up in. It was just the state I went to, right? There's no way to get to another state. So that's why none of that complexity was there. So now that we have that, we have VS as this. We've computed our value, and then it's the same sanity check as before. I'll just copy this in because nothing else changed. There we go. If our value function, or if our estimate for the values is no longer changing, then we're good to go, right? We have kind of completed our updating of the values, and we can return our values. And so we end up with, looks like I gamma. There we go. So this is my current estimate for the values, just like that. And now that we have all that, we have to repeat exactly the same process for our improvement. So this time, let me just go ahead and copy our policy improvement function. So that's still this, right? Policy improvement. Nothing crazy is changing. It's just that instead of directly, and let's call these the values, is that? So instead of just directly computing our Q values, we again need to accumulate up for all the possible places I could go. So let's go ahead and do that. So we're going to go ahead and get rid of this. So we're going to, instead of saying for action, we're going to call this for wanted action, right? For the action I want to take, like sure, I want to go down, but I may actually not. And so now that we have that, we can do, we can call this the possible taken actions, again, env.unwrapped.p for this state and for this wanted action, right? The thing that I actually want to do. And then we're going to create a QSA is going to be 0, just like that. Go ahead and now we're going to accumulate. So again, for prob s next reward and terminal in possible taken actions, so it's exactly the same as before, our QSA, and we're just going to accumulate in exactly the same thing. The prob times our reward plus gamma times the estimate of our future values, S next, right? Because again, nothing changed. It's still the same, everything is the same. It's just now we actually need to take the sum over all of the possible places I could end up in. And then once we have that, pick the action that gives the overall most value, even when there's some random chance of where we could end up going, right? So that's all this is. So this is just me accumulating up. And once I have that, I can do QSA.append QSA, right? Go ahead and store that. And our best action, everything else should stay the same, right? So the only novelty or the new thing is just accumulating up for all the places I could end up in. And so now we can run our policy improvement on these values. And so these are my updated policies. And so let's go ahead and try a stochastic game. So I'm just going to copy some of the stuff in. So this is my stochastic game. I guess I picked it doesn't really matter. The gamma, in this case, this environment is so simple that the gamma doesn't really change anything. And that's my current policy, right? Randomly initialized. Actually, no, this is not randomly initialized. This is the learned policy. So we reran the policy iteration, but on our new function. So we have a policy evaluation function, policy improvement function. So this is our updated policy. This is our policy. And this actually kind of makes sense. Think about it this way. if I want, for example, if on this step, remember this location here was a frozen lake. So if you fall in here, that wouldn't be good. Notice how smart this method is. This is saying go left, right? Which doesn't make sense. Like, what's the point of going left here? But the key idea is that if I go left here with 30%, 1/3 of the time, I'll go left, which means I don't move at all. I'll be stuck here. 1/3 of the time, I'll go up. Up is still safe, so we're good. And 1/3 of the time, I'll end up going down, which is safe, right? Because that's the randomness of this environment. Now, if we had gone down instead, let's say we went down, then 1/3 of the time I'd go down, which is fine. 1/3 of the time I'd go left, which means I stay in the same place. But 1/3 of the time I'd go right and I'd actually fall into a frozen lake. So going left is preferable than going down, because at least if I go left, I could accidentally end up going down. But if I end up going down, if I want to go down, I might actually end up falling into the frozen lake. And that's a really cool way of seeing how our model ends up learning some of these interesting dynamics in our system. And so let's just go ahead and play a bunch of games and just see. So whenever it comes to stochastic environments, the only way to evaluate how good the environment is by just playing lots of games and then seeing what proportion of the games you actually won. So we're just going to say num games is 1,000 and max, let's just say max steps is 500, right? And we're going to do game successes is 0. And we're going to do for blank in range games, or num games. Oh, ignore that. Num games. We're going to play a bunch of games. And for each of the game, we're going to do an observation. It's going to be, all right, we're going to start the game equals env.reset. So go ahead and start a new game. And then for blank in range max steps, so we just don't take too many steps. We're going to take an action. So the action is going to come from our learned policy. Int learned policy for this state, right? So what is the policy prescribed for this specific state? What action should I take? I'll actually take this step. So observation, reward done, truncate, and then just extra information that we don't care about is env.step. There we go. And we want to make sure we take the action, right? So the action that we selected. And then we can check if done or truncate. I actually don't know why I even included max steps in here. We don't use it for anything, so there we go. Or no, we actually do. Right, so how many steps of the game we want to play? It's fine, don't worry about it. So if done or truncate, right? So if the game's over, then we can do if reward is greater than 0, so we actually got some reward. Then we're going to do game success plus equals 1, or successes, right? Game successes. That means we won a game. Because remember, the game only gives a 1 reward for getting to the end and 0 everywhere else. So if you won, then you got a 1. If you didn't win, then you got nothing. And we can also throw a break in here. The game is over. And so now our proportion successful, right, is just going to be game successes, or yeah, game successes divided by how many games we played. And we can see that looks like we made a mistake here. This should be observation, not state. And there we go. And we can see we won 73% of the game, which is actually pretty good, because if in this game, if you take a step, you're only going to actually take that step 1/3 of the time. So the fact that we can still win the game almost 3/4 of the time isn't too bad. So either way, this is the setup, right? This is basically our policy iteration method, our first kind of foray into reinforcement learning, an actual application of it. Again, policy iteration and value iteration that we're going to look at next time is not so useful because it's a model-based method, and in most real-world scenarios, you don't have the model of the environment, because if you had the model of the environment, then we wouldn't be working so hard to do all this stuff. But either way, this is basically our first attempt at trying to solve this very simple environment. In the next one, we're going to look at value iteration, so I will see y'all in that one.